You have just done some calculations and learned how to perform emission inventory and calculate different scenarios. In this video, we will discuss carbon tax and marginal abatement cost curves. In theory, pricing carbon will encourage travelers to use vehicle fuel types that pollute and cost less per mile or kilometer of travel. Electric vehicles are a prime example. These vehicles have much lower fuel costs than gasoline vehicles, even with low gasoline prices that we experience today. Let's assume that an annual fuel cost for Toyota Camry is equal to $950, while for standard range Tesla Model 3, it is equal to $500. If gasoline is additionally taxed because of its high polluting properties, the annual fuel cost difference between gas-powered vehicle and an electric vehicle will widen. Although the added fuel cost resulting from a carbon price would increase this price gap and encourage consumers to consider electric vehicles, this effect would likely be small, given a carbon price of, say, $50 per metric ton of carbon dioxide. This is one of the main reasons why effective pricing of carbon is so important. Just like in other sectors, mitigation potential is studied in transportation. Let's recall the definition. Mitigation potential is the quantity of net greenhouse gas emission reductions relative to a specific emission baseline. It is often expressed in cost per unit of carbon dioxide equivalent emissions avoided. Before we examine abatement cost curves in transportation, let's solve a quick example and evaluate annual emissions between sedan and an SUV. To do so, we have to make the following assumptions. Sedan uses 1,500 liters of gasoline per year, and SUV uses 20% more. 1 liter of gasoline contains 33 megajoules. Emission factor per gasoline equals 73 kilograms of CO2 per gigajoule. Annual CO2 emissions can be then easily calculated by making sure all the units check out and simply multiplying the assumed factors. So for sedan, we will arrive at 3,614 kilograms of CO2, and for SUV, we will arrive at 4,336 kilograms of CO2. You can immediately tell that SUVs emit more than sedans, even with the modest assumption of them consuming only 20% gasoline more than sedans, which in reality can be often much more than 20%. Knowing how harmful they are for the environment, costly in fueling, and controversial in transportation safety, particularly in context of pedestrian fatalities, we would expect their purchases declining. But is that really the case? Share of the SUVs in total car sales in key markets have been increasing. Each line on this graph indicates different region. United States is light blue. Dark blue is Europe. Light green stands for China, dark green for India, and lastly yellow for South Africa. The orange line indicates their increase globally. We got two options. First is do nothing, and likely seeing their number increase, and the second one is do something and hopefully decrease their number. Just like we compared the CO2 emissions between a sedan and an SUV, and we concluded that there are 722 kilograms difference between the two vehicle types, we can similarly look at how other technologies are evaluated. Just like in the energy sector that was discussed in the first part of this course, marginal abatement curves can be used to examine and evaluate different transportation options. Before we look further, let's recap the definition. Marginal abatement cost curves are the estimates of the volume and costs of opportunities to reduce emissions in a given year. Each box represents one emission reduction opportunity. The height of the box indicates the cost to reduce emissions, usually by 1 ton of CO2 equivalent. With this opportunity, and the width of the box represents the annual greenhouse gas emission potential in a given year. Opportunities are generally sorted by increasing costs of ton of CO2 to decreasing. When the marginal abatement cost is negative, it means that low carbon option is cheaper than the business as usual option. Let's now see different road vehicles and their abatement costs. Here on the graph, you can see two colors, light and dark blue. Light blue shows an estimation for a gas price at $60 a barrel, whereas dark blue for $30 a barrel. And the following technologies go from the left, and they go electric bus, electric 2-3-wheeler, battery electric vehicle, and a hybrid car. The higher the gas price, noted in light blue, the lower the abatement costs. Abatement costs for electric bus have much wider range than the ones for hybrid cars. It is also optimistic to say that some of the ranges go below the horizontal axis, meaning that the low carbon option could be cheaper than business as usual. Let's now look how transportation technologies compare to other sectors. On this curve published by consulting company McKinsey, you can see that the electric vehicles noted as city cars and EV sedans both have negative abatement costs, which as we defined to mean that low carbon option is cheaper than the business as usual option. And that is a huge opportunity. Even the EV SUVs place to have a marginally negative curve. According to this graph, aviation sector will face substantial investments in their efforts to decarbonize, as abatement costs for biofuel aviation are very high. In this video, we discussed the idea behind carbon tax and examined marginal abatement cost curves in context of transportation. We learned that many low carbon options are cheaper than the business as usual option. On a side note, electrifying our automobiles and transportation industry is just a fraction of the solution worth considering. To decarbonize transportation and provide societal benefits, we should first try to consider to remove as many vehicles as possible from our roads and electrify the remaining ones. Remember, although electrification partly solves the pollution, the space on our planet is scarce and congestion in our towns will remain to be a challenge. With that said, in the next video, we will talk about transport-related behaviors, define elasticities, and use them to perform some calculations.